All right, in part B, let's estimate the natural log of 1.1 using our third degree Taylor polynomial, which is this. That will be approximately equal to the natural log, near where it was centered. So, to estimate the natural log of 1.1, we will input 1.1 into our Taylor polynomial, and we get 1/10 minus 10 squared over 2 plus a 10th cubed over 3 over 3. This reduces to 143 1500ths, or about 0.0953 repeating. How about part C? In part C, we ask you to use the alternating series remainder theorem. To use this theorem, there are two conditions that must be true. First of all, it must be an alternating series. Second of all, the terms must converge towards 0, and every term must be less than or equal to the previous term. Normally, if we're trying to find an error bound for our series estimation, we would have to check these to see if we can use the alternating series remainder theorem. In this problem, however, I did not require that you show these because the problem just came right out and said, use it. And like I said, you didn't need to do it in this problem where I just asked you to use the theorem. But if you did, you needed to know the general form of these terms. And this was the general form of these terms. And now we can answer these if we needed to, but you didn't need to in part C. Anyway, if you did do that, or if you just would like to and appreciate the review right now, remember that this is a geometric series. And so if it's an infinite series, as n approaches infinity, it converges when x minus 1, or really negative 1 times x minus 1, when its absolute value is less than 1. When r has a distance away from 0 that's less than 1. So that means we'd be between here, which means we are only concerned about these questions on the interval of convergence of this converging geometric series. So as long as x is between 0 and 2, this converges, and if x is between 0 and 2, then this factor will be less than 1 to the nth power, bigger than negative 1, and n, as n approaches infinity, is growing toward infinity, so we can check this box off. And what about this box? We want to know if any term is smaller than or equal to the preceding term. This is true whenever x is less than or equal to, we add 1 to both sides, 2 plus 1 over n. So as long as x is smaller than or equal to 2, that is within our interval of convergence, this will be a true statement. We can check that box. But remember, you didn't need to do this in this problem because I just said use this theorem, which kind of implied that these things were true. But now you have a review of how you would check these conditions in a case like this, just for review. All right, so how does the theorem work once we know that the conditions have been met? The remainder, or the error, will be less than or equal to the absolute value of the first unused term. So the first unused term was that, and what is that equal to? When x is 1.1, it's equal to a 10th to the 4th over 4, which means that the maximum error is 1/10 to the 4th, which is 1 over 10,000, divided by 4, which is 1 over 40,000.